So this is a typical diode circuit. So what is a diode? What's a diode? It's not something very difficult. It's an electronic device. It's the simplest electronic device that allows the current to go in one direction. So the current in this direction cannot go. It just go in this direction. So this is the first thing. The second thing, when there is a current goes in this direction, there will be a voltage drop. Now this voltage drop and the current have a nonlinear relation. That's all. That's all you need to know. That the current that goes here in the circuit is equal to Is, a constant, times e to the power of Vd. Vd is this voltage divided by Vt, which is another constant minus 1. As simple as that. That's all you need to know. However, you will see that a diode can be. This is the real diode. This is the real diode characteristics. Okay. Now you will start talking about when you study the diode as an ideal diode. Okay. So the ideal diode can be having two different models. The first model of the diode, A, the diode can be treated as short circuit. So this is the first model about the diode. So if this is a short circuit, so your circuit would be something like this: Vs, short circuit, and an R. So this current I is basically nothing but your I is equal to Vs divided by R. That's it. Or sometimes you deal with the diode as having a fixed voltage drop, 0.7 volt. So your Vd is equal to 0.7 volt. Okay. So if this is the case, so this is your diode. So you'll have here 0.7 volt and R. In this case, your I is equal to Vs minus 0.7 divided by R. Okay. So these are the two models of the diode, ideal diode. And this is the real diode. This is the equation we wanna able to solve it. Okay. So let's see the example and see how we'll set the equation. We don't need to go more than this. And I will not ask you in the exam a question with the diode. But as I said, this is a part of the course that I like to include, which I call it the application. Okay, so the application in the course is very, very important, so that you really link this to your to the course. Okay, so let's see here. We have here this question: Vs is equal to 10 volt, R is equal to 1 kilo ohm. Okay, the current, we want to find this current I. Okay, and of course we will end up having a nonlinear equation. So we want to do iterations using the practicing techniques, the bisection method, until the absolute approximate relative error less than 0.1%. Okay, so we'll start with this equation: I is equal to Is, the one that I just showed to you, e to the power of Vd over Vt minus 1. Now, if we take KVL, this is your Vd, as I said, and this is your IR. So if we take a KVL here, your Vs is equal to Vd plus IR. This is your equation. KVL. This is coming from KVL. Okay. Now, to simplify this, I can assume that your I is equal to Is times e to the power of Vd over Vt, approximately equal to this. I can cancel that one, and doesn't have really a big impact. So this is now my equation. So divide by I of s. So I divided by I of s equal to e to the power of Vd divided by Vt. Okay, I will take ln from both sides. So take the ln here, take the ln there, then I will have Vt over Vt equal to ln I over I of S. I'm just establishing the equation. So your VD here is equal to VT times ln I over I of S. Now, I know, now this is my VD. I will go and substitute this VD in this equation. So your VS is equal to VT ln I over I of S plus IR. Now, I of S is a constant, VT is a constant, okay? And so what I have here, and R is a constant also is given, R is given to you, okay? So now I will have an equation, a nonlinear equation in terms of I. That's all. So this is my equation now that I want to solve for it. I want to find the roots of I. So if I substitute the values of I of S, which is 10 to minus 12 amp, VT is equal to 0.025 volt. So I will have this equation. This is my equation. Now this is the VS. So I will have this equation. Okay, substitute in the value. So my function now, f of I is a function of I. Now I want to make this is now in the form of f of I equal to 0. So I will move this to this side. So I'll have 10 minus the rest. This is my function that I want to find the roots of it. Okay, so here I have a completely circuit question. I reach to this nonlinear equation. So those nonlinear equations that we solve, they are the outcome of physical problems. Okay, so in our context as engineers, we have circuits, we have electronics, we have sensors, etc. So we have this relation there. Now, as I said, and I repeat this now maybe for the second or third time, you will not supposed to do these things in the exam. The exam, you will get this equation. The course starts from here. Once I know this, then I will start the question. But what I want you to know that these equations are not something very theoretical. These equations are something that derived from real physical systems. Okay. Now, the question is, I was asked this question yesterday. Now, when I have something like this, okay, what is the limits? If I want to use the bisection methods, what are the limits that I will use to solve for this? Because I have to have a limit, A and B, and I start the bisection taking the average, etc. Now here I have no clue what is the limit. Okay, so in practice, you have, by understanding of the physics of the problem, this is what I mentioned last time, by understanding the physics of the problem, you can know, you can find this limit. But for the sake of this course, these limits will be explicitly given to you. Okay, so now here, how I can find the limit? We know that this diode can be approximated as either a short circuit, meaning VD equal to 0, or as a 0.7 voltage drop, means VD is equal to 0.7. Okay, so I will solve the circuit twice, one with VD equal to 0 and find I, and second, when VD equals I1 and when VD equal to 0.7, I will resolve it and find I2, and this will be my limit. And we will check and verify this. Okay, so if we model with the shorts, if this is a short circuit, we know that your I, very simple, is equal to 10 volt divided by 1000 ohm. The resistance is a simple Ohm's law, so this is equal to 10 milliamps. Now, if VD is equal to 0.7 volt drop, then your I is equal to 10 minus 0.7 divided by 1000, which is 9.3 milliamps. So these are the two limits. To verify, that these are the two limits. What I need to find, I will find VI at these two values, at 10 milliamps and at 9.3 milliamps. Then I will multiply F at 10 milliamp times F at 9.3 milliamps, and I want to make sure, is this less than 0 as we expect or not? We are expecting this to be less than 0. Okay, so this is what I want to find. So I will find F. So I will go back to the function that I developed, and I will find the F at 10 milliamps. Okay, so this is equal to 10 minus 0.02. Just now direct application 5, 8, ln of 10 milliamps divided by 1 times 10 to minus 12 minus 10 milliamps times 1000, and this is equal to minus 0.594. If I find F at 9.3, this will equal to 0.1078. So as you can see here, we have at least one root between these two numbers, and this problem has only one solution, because the VD cannot be multiple voltages. It has to be only one voltage. So I know that my root is between these two. Okay, now I found the equation by understanding the physics of the problem. Second, I found the limits of my answer by, again, understanding the physics of the problem. This is when you deal with something practical. This is how you deal with it. Now, everything that was left will become pure numerical method. Okay, so now I will start with the first iteration. My current at the first iteration will be the average between these two values, which is 10 plus 9.3 divided by 2, which is equal to 9.65 milliamps. Now I need to go for the second iteration. Now the limit is between 9.3 so 9.3 to 10 milliamps. Now I found the solution here is in the middle. Now I want to know if this answer is between 9.3 to 9.65 or 9.65 to 10. So we need to know where is my answer here. So again, I know the function at 9.3. I know the function at 10. I already calculated that here, as you can see. So at 9.3 is positive, at 10 is negative. So I need to find the function at my new answer 9.65. And if I do the calculation, you will find this is a negative number, which is minus 0.243. So this is my function. So now I know that now this is positive and this is negative. Since this is negative, so I know that cannot be here. It has to be here. So the new answer is between 9.3 and 9.65. Okay, excellent. So now I will find the current as a second iteration, which will be the 9.65 plus 9.3 divided by 2, which is equal to 9.475 milliamps. Now I will find the error. Now since I have now two solutions, the current and the previous one, so I want to find the relative approximate absolute error, which is 9.475 minus the previous answer, which is 9.65. divided by 9.475 times 100. This is equal to the error, which is 1.84%. Okay. And now what's next? I go and evaluate the function and keep doing this until I reach to the required level. Now, since we understand the process, I don't need to solve it. Let's just go through it together here. So here, this is the answer I just found. This is the error I just found. Now we need to evaluate 9.475, and I found that this is a negative number. So the answer will be between 9.47 and 9.3. I go back here, find the third iteration, it's 9.388 milliamps. The error is 0.932, still higher than the value I'm looking for. I evaluate the function here, it is positive, so the answer now is between 9.388 and 9.475. And how this is look like, so we started between 9.3 and 10 milliamps. This is where we started. We found the first iteration. Then we found the new answer is here, 9.475. And then we found this answer, 9.388. And then we found this answer, 9.431 milliamps. So see how the bisection is going here. And if I continue for more iterations, after the 7 iterations, I get an answer less than 0.1%, which is the criteria that I am looking for. Okay, so as you can see here, this method is very straightforward. It's mathematically is very easy to implement. It's very easy to program. Okay, so it's always converging, and the root brackets gets halved each time. So you'll find that even your error, you notice that the error is every time is almost halved. Every time your error is halved. You see here 0.46, 0.23, almost you are getting halved because you are always bisecting the answer. Now, what are the drawbacks? One of the drawbacks is that it has a slow conversion. And we will see that once we learn about fast converging methods, especially neutral rafter. You see a huge difference when it comes to the converging. So that's something that is very, very important for us. Now, why this is important? Because imagine if I have thousands of those nonlinear equations, then conversion rate become very, very important. Otherwise, the system may take very long time to converge or to find the solution, and sometimes you run out of memory. Okay, so you need a fast converging algorithm. This is something very, very important. Now, another drawback, if one of the initial guesses is closer to the root, the conversion is slower. Now, imagine that you are here. This is your limits, A and B. And then the answer actually was here, very close to B. Okay, but now what will happen? You will find the average, which will be here. So you are far away from your answer. Okay, so it would take it a while before it converges. If your answer is in the middle, it's faster to converge. But of course, you have no clue. You don't know is your answer closer to one of the limits or not. Okay, so this is one of the drawbacks. Another drawback, and this is one of the questions I was asked yesterday. The question is, if the function is something like f equal to x squared. So this is the function. So if you take any 2 points, okay, any 2 points, take here and here, here and there, here. So you take any 2 points here, A, B, B, C, C, D. Always you will have positive number, because the answer is here. You don't know that, okay? So if you have a function like a parabolic function like this, why I'm saying this, because the function will be always positive when you multiply f of a times f of b is more than 0. If you multiply any two numbers here, you will always have more than 0. If it is more than 0, then there is no roots, or there are multiple roots, even roots. You don't know. Okay, but there is one root here. But because the root here is the function has this shape, parabolic shape, you will not be able to find. And it could be, for example, x minus 1 square. Then the function will be shifted 1 to the right. But still, you have the same problem. Another issue, if you have a function like this, okay, so if you have like your limits here, a and b, then this will be negative, this the root positive. Then you would think that there is a root here in between, but there is none. Because this is, they will not never touch the 0. So you will never ever be able to find the root. So this is when you have, it is a misleading. It gives you an indication that there is a root between a and b, but actually it doesn't have a root. Okay, so these are the main drawbacks of using the bisection. So we start with something simple, easy, but it has its own drawbacks. Then we will go to the direct methods, which those methods that you will start with one initial guess. Here you don't have multiple 2 points to guess your solution, and then you have to have 2 points, and these 2 points, they have to be the right and left limits of the solution. The solution has to be between these 2 points. If the solution is outside, then you will not find a solution. So it has certain drawbacks. So let's see this method. Now, in the previous method, we put everything in that format. F of x is equal to 0. Now, we want to change the format in something different, that x is equal to g of x. Okay, so this is a different format. I need to play with the function so that I will put it in this format, not in that format. Okay. For example, in the first question, we have x squared minus 11 equal to 0. So this is your f of x. Now I need to put this in this format, an x equal to a g of x. And now this looks tricky for me. How I can go from here to there? I will come to it. But let's start with something very simple at the beginning. So for example, if I have a function like this, minus ln of x minus 3 of x plus 5 equal to 0, and I want to put it in. So this is in the format of f of x equal to 0. This is your f of x. Okay. Now I need to put it here. So I can, for example, move the 3x to the other side. So it becomes 3x equal to 5 minus ln of x. And then your x will equal to 5 minus ln of x divided by 3. So this is one way. Okay. Another way, so this will be in that format. So this will be your g of x, and this is your x. So you'll have an x. You want to find the intersection between x and g of x. Your intersection is your solution. Okay. Or I can say move the ln of x to the other side. So it becomes ln of x equal to 5 minus 3 of x. Raise both to the power of e. So this becomes x is equal to 5 to the power of, e to the power of 5 minus 3 of x. Again, this now becomes your x, and this becomes your g of x. So there are different ways. As a matter of fact, there are an endless number of ways. And later on, we'll see, okay, which one to use? Should I use this or this? Or it doesn't matter. Maybe all of them are good. Okay. Now, once I set the equation like this, then I will start with my initial guess, with my x of 0. This is an initial guess. I have to come up only one number. Okay. Now, once you find you start with this, then you find your x1. So your x1 will equal to g of x of 0. So you come here or here. So you'll find the second iteration, which is x1. You take the initial guess and you substitute it here. Then you find x2 is equal to g of x of 1, and so on and so forth, until you reach to certain error. This is what called simple point iteration. It's very simple, and it is very close to Gauss-Seidel actually. Okay, for one equation. So let's see how we do this. Let's see how we solve this one. This is a nonlinear equations. Now, if I want to put this into the bisection format, it will become equal to 2x minus log of x minus 7 equal to 0. This is your f of x. Then I have to find two boundaries for the solution, and then I will have to use the bisection. I don't want to use the bisection method. I want to use the simple point method. So what I should do, I have to put it in a form of x is equal to g of x. Okay, and here it says I want to keep on working until I have 5 decimal places. You could have different criteria here. The criteria is you want to make sure that your answer is correct for 5 decimal places. Let me just please just a second here. Let me shut down the email because it's annoying. Okay, let me just shut down the email. Okay, good. So let me go back here. Let's go back. Okay. So I want to put in this format. So it's very simple. Take the one way to do that. Easier way is to have that as x equal to 1/2 7 plus log of x. So this is now my g of x. Now I have to start with an initial guess. Okay. So let's say that our initial guess x of 0. Now we'll see later on that the initial guess and the function has an impact, especially when you work with something like interruption, but this we'll talk about it later on. Okay, so let's say this is equal to 1. So this is my initial guess. Your x1 will equal to g of x0, which is equal to 1/2 7 plus log of 1. This goes to 0, so this is 3.5. So this is my initial guess. Now I will go to equal to g of x of 1, which is this one. So we'll take this one and substitute here. So it becomes 1/2 7 plus log of 3.5, and this is equal to 3.772,034. Okay, now I will find x of 3, which is g of x of 2, which is 1/2 7 plus log 3.77, the whole number. So you'll get this is equal to 88287. The criteria says I want to see the answer for 5 decimal places. So here we have only 1 decimal place is correct. Okay, then I will go for G4. We'll continue. So this becomes 3.789. So we have 2 decimal places, and so on and so forth. So it is very, very straightforward, very simple, that you can find the answer in that. Okay, so here all the answer, you'll find this one. Okay, let me check if you have any question before I move forward. I think there is. What is VT? VT is a constant called the thermal voltage. It's a constant value. Each diode will have its own function. Okay. From calculus, I remember that the bisection method can only be applied if the function is continuous on A and B. Yeah, of course. Yes, the functions I will give you to you, it will be continuous from in this, because as we have seen in the last drawback, when the function is not continuous at x equal to 0, there is no solution. So the function has to be continuous so that you will be able to find the solution. So that's correct. Okay, that's all. Now let's go for an interesting case. Now remember, this is in the format of the bisection method, f of x equal to 0. But I don't want to have this format. I have to have it in another format, which is x equal to g of x. Now, when we have something like this, it's not really easy to be able to find it, okay, directly. What we do actually, what if I add x to both sides? So this becomes x equal to x plus cosine of x. So I just added x to both sides. I didn't do anything. I did not change the function. It's the same function. And now this becomes my g of x. So sometimes, if it's not explicit, if it's not very obvious, then sometimes I need, or I have to do that. I have to do a little bit of manipulation to be able to do this. Now I could have it as 2x equal to 2x plus cosine x. So x is equal to 2x plus cosine x divided by 2. This is another way of doing the same thing. Or I can have different formats. So let's see this example. This is the same example we solved in the bisection method. Okay? And we start with x0 equal to 3. Now we know that the root is around this. Now if you know where is your answer lying around, then you start with something close by. That's making the conversion faster. Okay? Now when we have x squared minus x, like how to deal with this? Okay, so I can have different ways. I can say, let's say, 4x equal to 4x minus x squared plus 11. Okay, then your x is equal to 4x minus x squared plus 11 divided by 4. So this is one function. Or I can say that this is equal to x equal to x plus x squared minus 11. So this is your g of x, and this is your g of x. Now let's try to solve both. Does it matter? Does everyone or every formula will take us to a solution or not? If it doesn't matter, then that's okay. If it does matter, then we have to understand how I will select my g of x. Okay, so let's start with the first function, which is this one. Let's start with this one, and we said that if you remember, we said we'll start from 3 and 4 for the bisection method. Now we'll take 3 as our common factor. Okay, so your x of 1 will equal to 4 times 3 minus 3 squared plus 11 divided by 4, and this is equal to 3.5. X of 2 will equal to, now I will take this and substitute 4 times 3.5 minus 3.5 squared plus 11 divided by 4, and this is equal to 3.1875. So I start with a 3, the answer jumps to 3.5, now goes down to 3.1875. It seems it is working. Okay, go for x of 3, so it is 4.3.1875 minus 3.1875 square plus 11 divided by 4, and this is equal to 3.397. So obviously we are converging, and if we do more and more, so you can see here that the answer is really converging, and you will find that the conversion rate is a bit faster than the bisection method, which is good. Okay, so very good. Okay, let's see the other function. Okay, doesn't really matter. Okay, let's see here. So now this is my g of x. Okay, so first iteration, I will go. Let me answer a question before I solve this one. I think I have a couple of questions. In your first square, let me check. Will you? Okay, let me see this one. I don't know. I cannot trace it back now. Sorry. 2x square. I'm not. Oh yeah. I get you. Oh, this is wrong. Thank you very much. It has to be minus x squared. There is no 2x squared. You are right. Thank you very much. Okay. So that's for this question. The second question says, will we have to determine the initial guess or range of values by ourselves? No. The same concept that I told you about when it comes to initial guess. When you have the, I gave you the range of the answer. I told you I will give it to you. Now I will also, for this one, I will give you the initial guess. Okay, so for both cases, I will give you the initial guess, so you don't need to worry about it. Okay, so this is something very important. Thank you for this question. Now let's go back here and see this question. Okay, so this is my g of x. I will find x of 1, which is equal to 3 plus 3 squared minus 11. This is equal to 1. Okay, not bad. X of 2 now will equal to 1 plus 1 squared minus 11 is equal to minus 9. Okay, doesn't sound promising. Let's say x of 3, which is equal to minus 9 plus minus 9 square minus 11, and this is equal to 61. So you see here, it's very obvious that we are not converging. X of 4 equal to 61 plus 61 square minus 11, and this is equal to 3077 months. So it is very obvious for me that this answer is not actually converging. Why is that? This is the question now. Okay, so the criteria for this, and this is something very important, and this is, you'll see that for every numerical method, sometimes it does work, sometimes it does not. So we have to understand why it's not working and why it is working. So the answer will converge if g prime of x is less than 1 in the region of interest. Okay, in the region of where you will find your answer, it has to be the absolute value of the derivative of g of x has to be less than 1. Okay, if it is more than 1, then your answer will not converge. Okay, so if you look here, the region of interest meaning the initial guess. At the point of where you want to start your guess, the function has to be, its absolute value has to be less than 1. So if you find here, check here, take the derivative, this becomes equal to 4 minus 2x divided by 4, substitute 3, so it is 0.5. It is less than 1. On the other hand, if you take the derivative here, this becomes 1 plus 2x. So if you want to find g prime of 3, this will be equal to 1 plus 6 equal to 7 greater than 1. So this is will not converge. So this is like, so when you do your function, you have to align your derivative. You have to select a function that taking the derivative of the region of interest, region of your solutions, region of your initial guess is actually less than 1. If it's not less than 1, then your answer may not converge. Now, this is the last thing I will do. Let's see that in a graphical format. Okay, remember my function is x equal to g of x. So I have two curves, y equal to x and y equal to g of x. So this is my y equal to x and my y equal to g of x. So this is my answer here. Okay, I think this is a good question to address here. So can't you just select a different initial guess for any function, or in the region both the solution and the initial guess? You have to make sure that your solution, actually the initial guess has to be around the solution. This is where your solution. So if your function solution, when you try to do that, is away from its derivative is more than 1, then you will not converge. Okay, so it is a combination between where is the region of interest and the derivative of the function. Okay, so here this is my y equal to x and this is my equal to g of x. So this is the solution. So if I start here at x of 0, this is my initial guess. I will find the function. This is my function. Then I will find y. I might find x1. From x1, I will find g of x1, 3. So you can see the answer is actually converging. If I have, this is the function, and this is y of x, and I start here at x of 0. Okay, so you'll find x1 here. This is your x1. Then you find the function x1, x2. So also you are converging. Okay. Now when you go here, and if the function is the opposite, the function is at when you start. Now, if you, I will come to this. When you start here, now take the x0, x1, x2, x3. You are not converging. Okay. So if you start your initial guess, let's say here, then you might converge. Okay, like this, then you will converge. So where is your initial guess with respect to the solution is also something very, very important, and here will diverge as well. Will symbol 1 point stop working because if your derivative is more than 1, then you will not converge. Your answer will diverge. Okay, so I will stop here. So this point has a very it's a faster rate, easy to implement, but it has a very bad drawbacks as we have seen here, and it is tricky. Sometimes it becomes very, very, very difficult to find the function that can be used, or the function that it can satisfy the condition. You have to play with different things until you find your function. So it is easy to implement, but on the other hand, it has its own disadvantage.